Welcome everyone to our virtual public talk series. Hello, I am Lucinda Offer, Education Outreach and Events Officer at the Royal Astronomical Society, which encourages the study of astronomy, solar system science, and geophysics. I am very excited to introduce to you our guest speaker today, Dr. Olivia Jones, who will be telling us about the highly anticipated James Webb Telescope. Dr. Olivia Jones is an STFC Webb Fellow based at the UK Astronomy Centre at the Royal Observatory, Edinburgh. She received her PhD from the Jodrell Bank Centre for Astrophysics in 2013, and then worked at the Space Telescope Institute, the home to Hubble and Webb mission operations. And she's an expert in infrared astronomy and researches the beginnings and ends of stellar evolution in nearby galaxies. She is currently a member of the Webb instrument team and will be supporting its launch, commissioning, and first observations. A quick reminder that there will be a Q&A after the talk, so please get your questions ready. There are places to post your questions for our speaker in the Q&A box if you've joined us on Zoom, and in the chat box on YouTube. I also want to tell our viewers here on Zoom that we have enabled transcripts, so if you would like that, you can turn that on yourself in your user interface on Zoom. And thank you everyone for being here, and thank you, Dr. Jones, for being with us today. On to you.
Hello everyone, thank you very much for the warm welcome and joining me today when I get to talk about this wonderful new telescope we're launching, the James Webb Space Telescope, or commonly known in the future as Webb. This, I think, as you can see, as this video plays, is an absolutely stunning telescope and is going to be delivering cutting-edge breakthrough science over the next decade or so. And it's a very exciting time because launch is in, I've got this countdown to launch, is in just around 2 weeks' time. So this is a great time to be talking about this wonderful, exciting telescope of which I've been heavily involved in for about the last 10 years or so. So in the talk today, there's a couple of things I want to talk to you about. I want to talk to you about the challenges and technology involved in building the biggest eye in space. And the other thing I want to touch on a little bit is the science revolution that Webb will provide. So for those of you who haven't heard of Webb before, I hope to change that right now. We're going to give you a quick primer on everything you need to know. Webb is going to be the biggest telescope launched into space. And because it's so big, that means it's deployable. So it has to be folded up before it can be put in the spacecraft. It's going to be operating in the infrared, so not at optical wavelengths, in the infrared, which is more like heat radiation of the universe. And it is going to be 6.5 meters in size across the mirror, whereas its sunshield, this silver structure in the images, is actually going to be about a tennis court in size. Because it works in the infrared, it needs to be cryogenically cooled. So that's what the sunshield for. And then there's a cryo cooler involved as well on the telescope. And launch, the big exciting thing right now, is on the 22nd of December, 2021. And it's so great to be able to say that launch is so soon. And launch is going to be occurring from French Guiana on an Orion 5 rocket. And what we're going to do is send Webb approximately 1 million miles away from the Earth to a point called L2. And that journey takes approximately a month to do. And the mission goal is 10 years, 5 years minimum, 10 years is the goal at least. And it's a joint mission between NASA, the European Space Agency, and the Canadian Space Agency. So there you go, that's Webb in a nutshell. So the question is why are we building Webb? Why are we going so big? And the way to do this, and the reason why we're doing this, is to win at astronomy, you need two things. You want to be building bigger and bigger telescopes to make new discoveries, and you want to look potentially with these bigger telescopes in new wavelength space. So they're the two key factors to improving astronomy discoveries. And I think I can convince you that Webb is big. I just want you to gaze for a moment. This is my absolute favorite picture of Webb in one of the clean rooms. And as you can see this wonderful gold mirror. It's very thinly coated with gold at the front, but actually most of the mirror is made out of beryllium, which is a very light material, but is also very stable at cold temperatures. And then, so that's that stunning gold part. And then underneath the mirror is this silver and pink sunshield. And I hope you can see just how big Webb is. If you look at all these people working on their computers in the background or having a little break around a table at the corner. So yeah, Webb is big, really, really big. And so that's put lots of technological challenges in its building. But yeah, this is my absolutely favorite picture of the telescope. And just to put this in context of other telescopes you may have heard of, Webb is the revolutionary new telescope that's going to be launched. But in many respects, it's been billed as the successor to the Hubble telescope. Now, the Hubble telescope has done fantastic science for 30 or so years and is approximately the size of a double-decker bus. Its mirror is 2.5 meters across compared to Webb's 6.5 meters, but it does absolutely groundbreaking science, but at optical wavelengths. The previous infrared telescope, of which I have much love for, and one of the other great observatories by NASA, was the Spitzer Space Telescope. And Spitzer was absolutely tiny in comparison to both Webb and Hubble. Spitzer's mirror was around 85 centimeters. 85 centimeters, that was the cutting edge of infrared technology, and we're going to instead to a 6.5 meter telescope. And Spitzer was, I always say, about around the size of a small sports car. So just for perspective, we have Spitzer, which is the size of a sports car, Hubble, about the size of a double-decker bus, and then Webb, which is a tennis court plus a house attached together, all been launched into space. So just to give you an idea, Webb is really, really big, and is possibly the biggest telescope launched for a very, very, very long time. So that means we can't just use a normal circular mirror. That means the mirror has to be made up of components. And this is the clean room at NASA Goddard. So several years ago, this is the assembly component video showing the mirror of Webb being put together. All these 18 hexagons being moved in position over several months. So I'm glad this is sped up. And I was at the time based at Space Telescope Science Institute in the USA, just down the road from where Webb was being assembled. And every single day, one of my colleagues put up a new picture of this process happening on the notice board outside. But what you can see here is the engineers, the mirrors have are covered to protect them during this process. This wonderful machine structure, taking the mirrors and putting it into place. You may occasionally see a person pop in and out to try and do the electronics of putting all the mirrors in place. And together, the mirror plus electronics is around 40 kilograms in each segment. But this is a very complex process, but I absolutely love this video of the assembly of the mirror. And when Webb is launched into space, all these mirrors will very, very tinily move to actually focus the telescope. So when it's launched, they won't all be in focus, but that process will happen by focusing and observing some stars and then making some electronic connections. Just as we're going in, to just have a zoom in this process to give you an idea just how big each one of these segments is. Here's an engineer wiring up one of the mirrors, so it will operate on the telescope, and I just love this picture, just a close-up of the process. And then yesterday, while making the final slides, I found this new picture of the mirrors I've not seen before, and I just think here's with all the lens caps taken off, you can really see this really fantastically polished, perfectly smooth surfaces of the mirrors in close-up, and I just love this picture as well of the surface of the Webb telescope. There's no way most people that will ever get to be this close to Webb. So I think I've convinced you we have built a big telescope. Webb is very, very big. So the next option in how do you run into astronomy is to look at different wavelength coverages. And by wavelength here, Webb is an infrared telescope. And by infrared light, this is slightly at longer wavelengths than what you see with your own eye. So most of the sun's light is most of the sun's energy is in visible light. And so we can see that on a fantastic day when there's rainbows around, or there's some great album covers that has a fantastic picture of a prism and the light being split up into its components. But infrared light is just slightly longer. That means it deals with slightly cooler components than our sun. And so infrared light is heat radiation. And I can't resist ever talking about infrared light without showing a picture of a dog with an infrared camera. The picture of a dog is that lots of people know dogs' noses are very cold. So that's why in this picture that it's very dark and the eyes are very bright. And where the armpits of a dog are as well, that's also very bright. You can see the heat radiating off a dog. And I have an infrared camera because I've worked in Webb for so long, and I do like taking pictures of animals. So I've been on a hedgehog hunt just before they've hibernated. Unfortunately, though, my pictures haven't come out as great to show you an infrared hedgehog instead. So it's dogs for the purpose of this illustration of what infrared light is. So I just want you to remember that it's slightly longer wavelengths than the sun, and it's heat radiation from the universe. So what does that really mean in terms of astronomy? If we're looking for heat radiation, well, this is my absolute favorite constellation in the sky, the Orion constellation. And what you can really see here in the visible light is you can see these bright blue stars that forms up the arms and the belt. And then you can see one of my favorite stars at the top. It looks a bit of a different color, Betelgeuse. And Betelgeuse in the last year or so got very exciting for astronomers during the Great Dimming event. But Betelgeuse is very different from the other stars in Orion because it's a red supergiant. And that means it's slightly colder than these other stars in the system. So at this optical wavelength, Orion is stunning. But in the infrared, we have a very different view. Here we go. This would be a good time to maybe try and spot the difference. I'm going to give you 5 seconds to think to yourselves, what do you notice difference between the visible image and the infrared image of Orion? Okay, as we're online, I can't get you to yell this out, but there's a couple of things I actually really want you to notice. First things first, all those fantastic blue stars, these really, really big stars in the belt and around Orion have gone in the infrared. Notice they are not there. You don't see the stars, or you don't see these blue stars. What you do see though is Betelgeuse, this red star, this cooler red star, which is surrounded by dust, is actually still bright in the infrared. So this is part of the cool universe. And then something else that actually really stunningly pops up is in Orion's belt, you have a lot of star formation occurring. Stars are being born. You may have heard this before in this nebula region in the belt. I hope you can see my cursor. But what in the infrared, the region sites of star formation are really, really bright. So the infrared is great for peering through dust. It's like peeling back the layers of an onion to get to the core. You can see right through different objects until you see the heart of things. And these cooler processes, sites of star formation, the death of stars, the very first light in the galaxies are really, really bright in the infrared. And so that's why going to new wavelengths gives you new discoveries. And so I hope when you look at in the night sky, if you can see it, if it's above the horizon in the winter, for you have a look and you think about not just the visible view, but the infrared view of this amazing constellation where stars are being born and dying in the same region. In terms of astronomy, Orion is fantastic, but we also want to look at other processes in the universe. And so here is just an example of a nearby galaxy. A stunning galaxy, looks absolutely beautiful. On the left is a visible image taken with Hubble. Right is state-of-the-art infrared image of this galaxy taken with Spitzer. And again, as I remind you, the Spitzer telescope was very small in comparison to both Hubble and Webb. And again, it's another chance to spot the difference. What I hope you can notice in the Hubble image is in this galaxy, you have these dust lanes throughout the galaxy, these very dark patches. But in the infrared, these same regions are really, really, really bright. And as before, the really bright red are sites of star formation, which you just cannot see in the visible image. Also, these dust lanes, you can now see through this. You can actually see the individual stars. You can see the components of the galaxy, which is very cool. So in the infrared image, the blue light is from stars mostly. The green light is for something called PAHs, and that's polycyclic aromatic hydrocarbons. It's a bit of a mouthful, but really what you think about that is they're a trace of star formation, energetic processes, and actually also smells a bit like burnt toast. So whenever I see green in these infrared images, I think of a burnt toast type smell. And then the red are your new stars that are being born or your very cold dust. But what I hope we can also appreciate in this picture is the Hubble image is much crisper. It's got a better resolution. You can see the detail. It's much more clear. Whereas in the infrared image, you don't see as well. And that's because the telescope size, but also as you go to longer wavelengths, you need to have a bigger mirror to get the same resolution in your quality in your picture. So Webb will absolutely knock out of the water images in the infrared. They'll have the same crisp and resolution as Hubble. And so you'll be able to compare these two phenomena, these different wavelengths, almost identically, which is absolutely groundbreaking for infrared astronomy and the phenomena there. And in some instances, in fact, the pictures will be better, the clarity will be better than the Hubble resolution. So as you've probably all seen very stunning Hubble images, I'm looking very much forward to the next decade of stunning JWST Webb images of nearby objects. So just as I mentioned before then, we're in an absolutely new, we're not in a new wavelength, but we built a bigger telescope in a new wavelength. So we have Hubble that operates in the ultraviolet and a bit in the visible and a tiny bit in the infrared. Then Webb has some overlap with Hubble. It has some overlap in wavelength with Spitzer, but will absolutely revolutionize that wavelength regime. And so we're expected to make many new discoveries and cutting edge science areas. And then Spitzer, that very small telescope, operated at much longer wavelengths as well. So we won't get a replacement view for that, but there is overlap with both Hubble and Spitzer. And Webb is going to make, the potential for Webb here is amazing, and I cannot wait. So I hope I've convinced you that we've built a big telescope and we've got new wavelengths. But there are challenges involved. As I've mentioned before, infrared light is heat radiation. So if you're trying to observe the cool universe, but you also have a very strong detector in the infrared, which we've built, how do you stop the heat from the sun and the telescope, in fact, itself, overwhelming that very faint cold light from the universe of what we're trying to detect? And there's two things we do here. One of them is we build a sunshield, this tennis court size sunshield, and that is the equivalent to putting on sun cream with an SPF factor of 1.2 million. So no factor 50 for Webb, it's a 1.2 million equivalent by putting in a sunshield. And then the other thing we need to do is put it a long way from the sun. The further away from the sun you are, the cooler it is. Therefore, the less heat from the sun will be overwhelming your detectors in the telescope. So Webb will never, ever, ever face towards the sun because the heat would warm up the telescope. It always needs to face away from the sun. And just to give you an idea of what the 5-layer sunshield looks like is this video here. And what you can see is how big the sunshield is, the very thin material it needs to be made out of because it has to be very light as well. And then in space, this is all folded up for launch. And then in the first month or so, this 5-layer sunshield unfolds, which is slightly terrifying because this has to work to make Webb work. And the temperature, this is such an amazing piece of technology, the temperature differential between the hot side of Webb and the cold side of Webb is mind-bogglingly big. On the hot side, the side facing towards the sun, where the steering mechanisms are, the communications, etc., it's 85 degrees Celsius. But on the cold side, on the other side of the sunshield, because all the heat's been bounced out, it's minus 223 degrees Celsius. So it's really, really close to the absolute zero temperature of the universe there, just through this sunshield, this piece of technology. And just to give you an idea of this, we can see the sunshield in all its glory unfolded. This process was tested a few times on Earth to make sure it worked, because this has to work for Webb to work. And I hope you can see just how big the sunshield is for a start. And you can also see these wonderful layers arranged in it, not flat, but in this sort of V-shaped configuration to dissipate the heat away from the telescope. So I love this picture as well, because I think it's stunning seeing the sunshield and the primary mirror of Webb all combined together. So we've built the telescope. It's great. Now, the next thing to do is launch the telescope. So launch is in about 14 days. So I'm very excited, but also slightly nervous. And we're launching from French Guiana. So as you can see, it's located just above Brazil in the map, if you're not entirely sure where French Guiana is, on a European Space Agency Ariane 5 rocket. And so Ariane 5 rockets are great for this. This may potentially be one of their last launches because they have the biggest space inside the rocket, the biggest payload space. For manufacturing Webb, That's what it was built for. It's built for the Ariane 5 to launch it. No other rocket is capable of doing this. And so launch is in 14 days. And that process then is going to be that 3-month journey to its resting place at L2. And I know several people who are going to be at the launch site, and I'm quite envious of them who get to see this in person, but also I'll be terrified. So I'm glad it's them and not me. So where we are in this journey then. So look, Webb was shipped about 2 months ago. And many of my colleagues were vastly tracking the shipping lane across the Panama Canal. All the tests have been in place, and we're in the final launch preparations now. Then launch will happen, this 29-day journey as it unfolds in space. And then 6 months later, for 6 months, we'll be calibrating all the instruments, making sure everything is right, aligning the mirrors, making sure the final instruments cool down, which is the mid-infrared instrument. And then in 6 months' time, first light will be taken and the new data will be released to the world. So midway through 2022 is when you'll see the first images from Webb. And so in the process, we have to pack Webb up for the trip. This is its base in California. And then right now, before it could be shipped to the launch site, everything had to be folded up into its launch configuration. And bear in mind, the reverse of this process will be happening as it's traveling to the L2 point. As you can see, the primary mirror is being stowed away. The secondary mirror is just at the top where all those people are. That has to unfold in space. The sun shields are being all folded in. And I just absolutely love this video that we're really at this stage where Webb is ready for launch. And that's the state it's going to be until just over 2 weeks from now in this final configuration. And I think you can probably all agree that Webb looks rather stunning. And then on the other side, at the European spaceport, French Guiana, we have the ultimate unboxing video. So this is the clean room now in terms of launch preparations. It's gone through its journey on the ship. It's been videoed and documented and tracked by as many people as possible. It's avoided any pirates who were all worried about, I think, any decoy ships as well. Don't have to worry about that anymore. It's now safely at the launch site. Here, the final checks are in place. A couple of my colleagues went to make sure the instruments were working correctly. And so it's all unboxed. Within the last couple of days, the final processes have been occurring. The rocket has been gift wrapped. And by that, I mean all the logos for Webb have been put on the outside of the rocket casing. Here is the European Space Agency logo being put on and the Webb logo being put on. And then as of yesterday, Webb has been fueled. So it went to a special room for this because this is quite a dangerous process. You can see some of the engineers and technology people in these special suits. And then, yeah, the process of Webb fueling has been completed yesterday. And actually, it's the fuel for Webb that limits the lifetime of the mission. There's no coolant. There's new technology involved, like the sun shield and a cryocooler, means that it's not liquid coolant that determines the lifetime of the rocket anymore in the infrared. It is just how much fuel it has for moving around and pointing at different objects. So this is it. It's all ready. So in the next 7 days, what will happen is now Webb has been fueled. It'll be placed upon the Ariane 5 rocket in around 7 days to launch, so in a week from now. And then that fairing with all the stickers will go on the next day. And then the day before the launch, it'll be moved out onto the launch pad. And then launch happens, we're all excited, it's going to be great. And then after 30 minutes or so, all the components of the rocket are separated and Webb is on its journey into L2 and its orbit for the next decade or so. And just to give you an artist impression of what Webb will look like in the rocket, though I'm sure in a few days we'll actually have the real pictures, Webb will be nicely compact in its launch configuration right at the top of its nose cone, and then blast off will happen. And just the engineering challenges of getting such a big rocket, a big telescope into such a small rocket is just mind-blowing to me. And before I've mentioned its journey, and its journey is to L2. And to give you an idea what that is here you can see the sun, and then you can see the Earth. And as the Earth will orbit around the sun, the moon is here, and then Webb's orbit is further away in this very stable gravitational point called L2, and it won't be actually at L2 itself, it'd be orbiting around L2, and it orbits that around once every 168 days. And so this way, the Webb will always be, the Earth will always be between the sun and Webb, just to keep it cool as well, but also makes it easier for communication. And L2 has been a very successful point for previous infrared telescopes like Herschel and Planck, which you may have heard of before. So Webb is a long successor to go into this orbit to look at the universe. And that's great because it can see much of the universe in one go. It doesn't have to worry about orbits around the Earth like Hubble does. So Hubble's much closer to us, but that means the Earth prevents observing for large parts of the day. Whereas where Webb will be, you'll be able to observe 24 hours a day. But the problem is if anything goes wrong, and I'm touching wood here, it cannot be serviced by people. So we need to make sure everything was right in the process. And in this journey, there's a fantastic video that shows the sequence of what Webb will do in space. Here you can see the antenna coming out, the solar panels to just provide energies. It runs on batteries until that point when the solar panels come out. And then gradually, this very key process, and the bit I think I'm most terrified about, is the unfolding of the sunshield. This process happens gradually. I mean, there's lots of that very thin material, as you saw earlier. It is then tensed up, and then once it's tensed up, very gradually, the layers need to separate out into their optimal configuration to reduce the heat that we're potentially facing Webb. At this stage, still, the primary mirror, the wings of the primary mirror are still folded up, but eventually they will move to make the complete mirror. And the secondary mirror, here we go, the secondary mirror, focusing the light, will pop out. And that all needs to happen as Webb is traveling away from us. So eventually when it's at the L2, the only thing left to happen then is the cooling of some of the instruments. So what are the instruments on Webb? I've talked to you a lot about the engineering of building Webb, but actually what science is going to be done and how are they going to do this? Well, there's 4 main instruments on Webb. These are called NIRSpec, which is a near-infrared spectrograph, and that's where you break light into its small, tiny components of colours for analysis. And that lets you learn a lot about the chemicals in the universe. Spectrographs are extremely powerful, and that NIRSpec is one of the primary instruments for that. Then you have NIRCam, which is primarily a near-infrared camera. And what that will do is take those really high-resolution images of different objects, both nearby and in the very distant universe. And then the other real main instrument, and the one which I'm personally involved in terms of actually commissioning this instrument and making it evolve and work for science, is the mid-infrared instrument MIRI. And MIRI is both a camera for taking pictures of astronomical objects and also a spectrograph. It has both. And it also actually has a chronograph as well. And a chronograph is a bit weird as a concept. What this means is you block out most of the light of the object you're observing. So if you want to observe a star with a planet, for instance, the chronograph blocks out the light from the star, so you can get this high contrast image of actually any orbiting planets. And so they're very, very clever piece of technology. So they're the 4, and the final instrument, sorry, I forgot, is NIRIS, the near-infrared slitless spectrograph. And that's a backup for NIRCam in case anything goes wrong, because NIRCam is meant to be one of the main workhorses of Webb, and that's needed to align all the mirror segments. So it's important for guiding the telescope as well as the science it will produce. And where do these instruments work? Well, 3 of the instruments, NIRCam, NIRSpec, and NIRIS, all work in the near-infrared. That's 1 to 5 microns. And at those wavelengths, you'll be looking at the cooler, redder stars, you'll be looking at galaxies, and you can see through dust in the universe. So you can peel back those first layers and see through dark patches. Whereas the mid-infrared instrument, the MIRI, is the only one that operates at these longer wavelengths. And that works then from 5 to 25 microns or so. And MIRI is perfect for looking at planets, comets, asteroids, the coolest dust, and things called protoplanetary disks. So these are disks around stars that are being born, where planets are starting to form. And it also has dust warmed up by starlight, as opposed to dust from the looking through dust in the universe. So this sees the coolest phenomena, and is the instrument likely to see the very first light in the universe. And because MIRI is in the mid-infrared, it needs to be cooled even more than the rest of the instruments. It's cooled to 7 degrees Kelvin. That's 7 degrees above absolute zero temperature in the universe, the point where atoms don't move anymore. And so MIRI will be the last instrument to be switched on properly and working and taking images and spectra. And because of this, and because it needs to be cooled, we've developed this new technology called the cryocooler, which doesn't require coolant to cool your instrument. And I think that's a fantastic piece of technology. And so MIRI will work for as long as Webb will work. And this is just this wonderful piece of engineering picture. You can see the people looking at the various components of MIRI as a close-up. So this is at the very earliest stages of Webb being put together. And to give you an idea of how an instrument like MIRI works, in the simplest mode, the imaging mode, you'll see a picture of the light coming into the instrument. I absolutely love this animation. It bounces around the instrument. This comes from the mirrors and the telescope. It bounces through here and is reflected several times and is focused onto the filter wheel. And the filter wheel lets you take very detailed colors of different parts of the wavelength regime of light. As you can see, the filter wheel moves and you'll take pictures as a slightly different wavelength. And that's how you get these stunning pictures of high resolution. It's not just broadband imaging, you actually focus in on very narrow wavelengths of light. And this has to be very compact and very lightweight to fit into Webb. There's equivalent for the spectrograph, but the light path bounces around, and that video is about 2 minutes long, showing the light bouncing around the instrument, but fantastic pieces of engineering. So the final part of my talk I want to touch on is the science. I've talked a lot previously about the engineering of Webb, and now I also want to talk about the science. Webb has 4 main science themes. The first one is to look at the end of the dark ages of the universe and the very first light produced by galaxies. And hopefully Webb and MIRI in particular will detect the most distant galaxy we'll ever observe and see the first stars. That will be an absolute ideal if we can see that. But even getting close to that boundary would be an amazing scientific breakthrough. Another component is the assembly and the evolution of galaxies. So how do galaxies form? How do they have the different shapes we see today? How do they merge together and collide? And it's not just the assembly, the physical structure, but also the chemical makeup of galaxies. How does it assemble as the universe evolves? So they're the more distant components of Webb's observing. As we come a bit closer, the 2 other main science themes are the birth of stars and protoplanets. So this is seeing how stars are born throughout the universe. And with Webb, because we can see through the dust, we can see right into the heart of star formation sites. This is going to be cutting edge, new discoveries. And the final science theme is looking for planets and the origins of life in the very nearby local universe. And hopefully we'll maybe be able to see the signatures of atmospheres of planets nearby with Webb. So I want to briefly touch upon the 2 themes which aren't my science interest, aren't my own personal science, but are very groundbreaking in their discoveries. And this is the first light. And so what we mean by the first light is, well, light in the optical and the ultraviolet, as we go further away from us, becomes redshifted. I'm sure many of you have heard of this. So if you want to look for this very first light and furthest away from us, you want to go to longer wavelengths. And this is where Webb will be fantastic. And so what we can really do with the technology and the detectors and the infrared sensitivity and how big Webb is actually we can look to around 20 million years or so after the Big Bang. So really we're looking for objects between redshifts of 10 to 20 with Webb, and hopefully you'll see many new discoveries in that regime in the future. And that will be fantastic by using the infrared cameras involved. Another area which is not my science focus, but I think is going to be groundbreaking, is looking for these life-bearing planets. And the way this works is that you have your star and your planet, and as this is orbiting the star, you'll take a spectra, and that's where you break the light up into its smallest components. And when the planet is behind the star, you'll see a different spectra to when the planet is in front of the star. And from that, you can subtract away the star spectra and get a spectra of the atmosphere of a nearby planet. And I think that's going to be very cool. So we'll be looking for things like water vapor and methane and carbon dioxide in the atmosphere of these nearby planets. And from that, so for instance, our own Earth spectrum has nitrogen, oxygen, carbon dioxide, and water vapor. If we can see the signature of that in a nearby planet, I think that would be revolutionary, and is something for you to be looking out for in the next decade or so. And then, as I'm giving a talk, I get to talk about my own personal science interests. And I personally am interested in star formation and the chemical evolution of galaxies. So here was me in very excited mode, with Webb folded up in the background when I got to visit its clean room. I wasn't in the clean room. It was nice components to keep you safely away from messing anything up with Webb in a viewing platform. But I was very excited to see Webb that day. Unfortunately, as I was driving, it was unfolded. And by the time I got to the NASA site, the telescope was in its more compact configuration. But even so, it was great to actually see Webb as it was being assembled. And thinking about the science I was going to do with it, because I'd already picked my targets for Webb by that point when I got to see it in person. And my personal science is interested in the life cycle of stars, how they're born and how they die. And to give you a crash course into the life cycle of a star, what happens is you have these very dusty clouds of gas and dust, and these are called star-forming nebula. And from this site, these are normally big regions of star formation. There's some in Orion, there's many in nearby galaxies, of which forms low-mass stars and high-mass stars. And we don't really understand that process in as much detail as we'd like. So, and this is hidden away by dust from the optical telescopes. Eventually, in the star-forming nebula, you'll start forming protostars. And then the life cycle of a star is determined by its initial mass from which it was born. A low-mass star, so a star like our sun, for instance, and up to 8 times the mass of our sun, is what I consider a low-mass star, goes through the process on the left. And this way it goes through this life on a main sequence, which our sun is now. It lives a long, happy life. Not much happens as it's on its main sequence. It's just nice and stable, great for life, long, happy. And then eventually, at some point, it hits its final phases of evolution, many, many, many years later, where it becomes a red giant. At this stage, the star starts to cool, and then it starts to pulsate. And as it starts to pulsate, it starts forming dust around it. And so this is what will happen to our sun, is it'll start to pulsate, it'll start forming different types of molecules, it'll get cooler. And by dust, I mean tiny little particles of sand, maybe some tiny particles of sapphire. Depending on the mass of the star, a bit heavier ones will form soot instead of sand around it in these tiny little particles. And eventually what happens is that material has a wind and is blown away into the interstellar medium between stars, and becomes a planetary nebula, of which there's many fantastic pictures. And eventually the core of the star will become a white dwarf and cool and become fainter and fainter. But the material it expelled during its lifetime and at the end of its life will go into the next generation of sites of star formation. And as it's gone through a process and there's been lots of nuclear synthesis happening in the core, it's got slightly more different chemical composition than what it was born with. And that process continues throughout the evolution of the universe. On the opposite end of the scale, you have high mass stars. So these are stars that are greater than 8 times the mass of the sun. And these are the live fast, die young stars. So they don't have a long, happy life, but they have a quick life and they burn out very quickly. Because they can burn out very quickly, you can see them. They're bright blue at optical wavelengths typically, but then as they die, they become more like Betelgeuse, that star in Orion I showed you. And again, they form lots of sand and sand around them, lots of molecules. Because they're massive, they can actually produce more chemical elements in their core in the fusion up to iron. And eventually stars will explode as supernova. And supernova are very, very, very bright. And in fact, one of the objects I'm studying is a nearby object called Supernova 1987A. And surprise, surprise, this is a star that exploded in 1987. And this is actually where we can learn a lot more about the death of the star and how potentially this may form a neutron star or a black hole. We've never seen that process happening in real time. And maybe with Webb, we'll be able to capture that first formation of a neutron star. And eventually, either way, material ejected from the supernova goes into interstellar medium, goes back into the star formation process, and this cycle continues and throughout the evolution of the universe. And so the very, very first stars were made out of the composition of the universe, what it was born in the Big Bang. That's it's mostly hydrogen, helium, and a tiny, tiny bit of lithium in the atmosphere of a star or in the star itself. But as the universe evolves compared to the sun now, there's a lot less helium. I mean, it doesn't seem a lot less here, shows you the amount of hydrogen and helium in the sun. The hydrogen is at 71%, whereas primordial hydrogen was 75%. But actually what you see in the atmosphere of these stars is you see a lot more oxygen and carbon and iron and other elements that weren't there in the very first stars. And so one of my research interests is tracing how that process occurs throughout the universe. And with Webb, I'll be doing that by looking at nearby galaxies. And I think some of the stunning parts of Webb is actually going to be the spectroscopy. The images will be fantastic, but I think some of the groundbreaking discoveries will be through the Spitzer instruments. And these are things that in the mid-infrared. This is the pillars of creation in the Eagle Nebula. And with spectra, which Webb has many of, you can see materials like water and methanol and carbon monoxide. And particularly one of the things that I look for a lot is carbon dioxide around stars that are being born. And that's a signature of stars that are being born in the very earliest phases of their life. And so Webb will actually be able to open the window of the chemical evolution of protostars and dying stars throughout the universe. And so it's a bit harder to intuitively understand the spectra, but you look for these squiggles and these very key dips. Some of them are subtle, that this is the tiny particles of sand I was talking about, little bits of methane, for instance. Just these key things are seen in spectra of different objects. And so just as I'm wrapping up, I personally will be looking at nearby galaxies, for instance, in the Magellanic Clouds. And these two pictures were taken by Spitzer, which I mentioned previously. And these have metal contents. And so I'm being an astronomer here, and by metals, I mean anything that's not hydrogen or helium, that are approximately half of what's in the solar neighborhood and about a fifth of what's in the solar neighborhood. And by looking at the stars in these galaxies as being born and as dying, you can actually study the chemical evolution of the universe and how star formation occurs under different conditions. And hopefully this then lets you infer how the first stars in the universe. And so I want to end my talk here. This is a compilation picture of all the objects that I'll be observing with Webb in the next year. These are the sites of star formation in the Magellanic Clouds in the top row. We have some nearby galaxies. This is called Sextans A. And this other galaxy on the left is called 1Zwicky-18. And 1Zwicky-18 has chemical abundances that are around a 50th of what is in the sun. So this is a galaxy that's forming stars at about a star a year. So it's very exciting scientifically. So I'm very much looking forward to this. And then as you go across, we've got two stars, Supernova 1987A and a Wolf-Rayet star. These are massive stars towards the end of their life. So we can learn a lot about these. And then at the bottom left is one of my favorite nearby planetary nebula, the Butterfly Nebula. And we'll be taking an in-depth look at the chemical processes that are occurring there. And these two other galaxies are NGC 6822, and we're looking at other Wolf-Rayet massive stars in other nearby galaxies. So this is just to give you a range of the science that I'm personally doing, and I'm looking forward to hopefully in the future sharing the equivalent image of this, but with a Webb view instead of a Hubble view or a Spitzer view, what you're currently seeing. So just to wrap up, Webb is going to be absolutely stunning. We've done a lot of engineering and technology to get there. I cannot wait for the science. Launch is in 2 weeks' time. If you want to get to a launch kit, which is provided by the European Space Agency with lots of goodies and information and things to play along with, the website and link is here. So I'll leave my talk there. Thank you so much for listening and letting me share with you the wonders that is the Webb telescope.
Fantastic. Thank you so much, Dr. Jones, and great to have a link there for people to get a launch kit. What do you know what that comprises of? I guess that's sort of the collateral materials.
Yeah, there's some videos in there. There's scientists explaining what they're going to do. I think there's some activities you can do. I think there's a wish Webb well things. There's a range of stuff and just information more about Webb as well. And so I think there's some activities and fun things and some more information if you're wanting to get more into the science of what Webb will do.
Yeah, fantastic. Thank you so much. So there's a lot of questions. I've done my best to triage them. So we're going to start with something that's kind of fun and maybe you probably already thought about or possibly know, but maybe cannot share. So please tell us if there's some things that are embargoed and you're not able to talk about. So Kate asks, where do you hope the Webb telescope, the JWS team, direct it first?
I wish I knew. I really wish I knew. It's absolutely top secret, the first targets that Webb will be taken. I know some people who know, but they're absolutely sworn to utmost secrecy. And so I think I'll find out at the same time as you will find out 6 months after 6 months after launch, when these very first images will be taken and released to the world. And in fact, released to scientists as well, so they can do science on these objects straight away as well. So yeah, I don't know. In terms of the stuff that I'm observing, a few of my objects are in the continuous viewing zone. And so I think personally, as if the timelines work out well, I'll be observing Supernova 1987A very early on. And I think I'll be observing the opposite end of the scale on the star formation site, NGC 346. That's the stunning picture that looks a bit like a witch. And I think that'll have to occur very early on in the mission as well. So I think they're the first science that I will get. I don't know what the first science the world will get, and I can't wait. Everyone keeps trying to find out what it is, but it's hidden carefully away from everyone, unfortunately.
Well, that was my follow-up question was how long will the public get to know? And so you said 6 months, that's how long we have to wait. Is that also how long we'll have to wait to see anything once it's in orbit in L2, or do we have to wait a bit longer than that?
That'll be the first science images. Along the way, I'm part of the commissioning team, so we'll be observing very bright stars to make sure the instruments are all working correctly, and making sure everything is as it should be, and if there is anything we can correct that. But no, the actual first science images will be 6 months. Nothing beforehand. It's all calibration targets and making sure we've got all our mirrors aligned. The Sunshield is working as we expected. All our instruments are working as expected. That's what happens in that 6 months. But in fact, most of that 6 months is not even the instruments working then. They still need to cool. Things need to settle down. It's lots of checks and moving telescope. So yes, 6 months is when the actual science really starts to happen.
Exciting. There's lots of technical questions here. I'm just going to jump into one of them. Jay asks, and again, you may not know everything, but just let us know. It happens. And why will Webb orbit around the L2 point as opposed to just sit there, which is kind of what we kind of use those points for, just to let less energy. And what they will also wonder, does Herschel or Planck also orbit L2?
Yes. So we want to orbit L2. Putting something specifically L2 is very, very difficult. And also you don't want to take up that one particular spot. It's a fantastic spot in the sky for putting telescopes. So having it, you don't want to just take that and then use it forever onwards if something goes wrong. So Planck and Herschel, Webb, all orbit it instead of rather being at that spot itself. It's optimal for both fuel consumption and keeping the telescopes cool. And then eventually, I think what Planck happened is it sent its final command and we actually moved it away from that orbit. And I imagine similar things we'll be doing for Webb as well. At the end, I don't want to think about the end of its lifetime, but yes, you want to keep that orbit as free of junk as possible. And I don't mean telescopes being junk, but once they've come to their lifetime end, you want to move them away, so you can keep that area of space available for more missions. It's so stable orbit. It's easy to get to in relative terms. So yeah, you want to keep it as pristine as possible, and we don't want to contaminate that orbit with rubbish as well.
Yeah, that's very considerate of space agencies to kind of make room for other science to take place there. And that is a kind of a question that did come up from Andy. Wants to know, what is the design life of Webb? Do you know?
Yes, Webb is guaranteed to run for at least 5 years. The limiting factor of the lifetime of Webb is its fuel. So it depends much. So ideally you want a 10-year mission. That's the goal. For instance, other telescopes had similar missions and been lasting much longer. I hope the same will happen for Webb as well. People at Space Telescope are very, very clever at making missions last much longer than their minimum lifespan. But on the way to L2, if any course corrections need to be taken, anything that needs fuel will limit the lifetime of Webb more. So we hope we've done all our calculations correct. There's 2 burn points en route where we can send some fuel. The less fuel we have to spend there, the longer Webb can last. As I've mentioned previously, Webb is very, very big. And that means moving it around space is actually quite complicated. It needs fuel to move it, to point at new targets. And what you really don't want is the momentum of Webb to cause a spin. So you need to be careful when moving around the sky, because the less fuel, and by moving around the sky, I mean pointing at different objects. So momentum management of the telescope is key as well to the lifetime of Webb. So it's the fuel lifetime. Hopefully, we've thought of strategies to mitigate using that fuel as wisely as possible. But a lot of it depends upon these 2 course corrections en route to L2 as the lifetime of Webb.
Yeah, there were lots of questions that came through about the fuel. What was its fuel being used for? Why isn't it using wheels to adjust itself like Hubble? And I believe I've seen that it is using reaction wheels to help move the observatory to wherever it wants to be pointed at. So, and so maybe the fuel, maybe you could tell us more specifically, is it to do corrections or things like that?
The fuel primarily is for the course corrections, but Webb is big. It's much, much, much bigger than Hubble. It has a lot of momentum associated with it. So if you start moving it, you can't just rely on the telescope itself. It needs fuel to actually move and stabilize itself. And after it moves slightly, it needs 30 minutes to settle down to stop all its moving parts from actually moving. And so this is actually part of the process of any Webb observations. And so you do need fuel for each one of those small movements. And that eventually, it's not just any gyroscopes that Hubble operates on. Hubble is much lighter, much nimbler, and Spitzer was even nimbler still. So I think of Webb, it's like trying to move your juggernaut truck compared to moving a tiny little racing Formula One car in space. So you do need fuel for part of that process.
Yeah, I suppose, that is kind of what also deals with the lifespan of a mission is once you run out of fuel, well, then there you go. So one question that one of our attendees, Chris, asked is, you compared it to Hubble and to Spitzer, and why not ESA's Herschel telescope, which is also in infrared? And I was looking at the range of each one. I don't know if you know much about Herschel in comparison. Go ahead.
Oh, I love Herschel too. I really do. My apologies for Herschel operated at much longer wavelengths. So from 70 microns plus so while Herschel did fantastic science, and I absolutely love Herschel, and I use a lot of its results, the reason why I didn't mention Herschel is it didn't have the overlapping wavelength coverage of what it did to Hubble and Spitzer. What I'm really hoping for in the future, maybe in around the 2040s, 2050s, is a successor to Herschel being launched in the equivalent size of Webb. But fingers crossed for that as a different science. The technology of putting that together and the thought process for longer wavelength successors has been thought about. The Origin Space Telescope is currently what it's known as a concept design. But yeah, it's a long way away before the long wavelengths that Herschel covered will be have equivalent of emission this size. So that's why I didn't mention it in this talk.
Yeah, I was looking at those. Herschel was 57 to 672 micrometers. That's quite a huge range compared to the 0.6 to and 28.5 of Webb. So Diane also asks, what's the rationale for not trying to cover the range of wavelength that Spitzer covered? Is there anything that we might be missing by not doing that?
The rationale is that, I love Spitzer. I really love Spitzer. But as you go to the longer wavelengths, you see cooler phenomena. And there's definitely many, many science cases for going to those wavelengths. One of the main rationales for Webb is trying to see the first light in the universe. And the wavelengths that will be, we expect to be, is around 5 to 10 microns or so in the mid-infrared. As you get to longer wavelengths, your images become crisper. The technology, when this was first proposed around 30 years ago, wasn't quite there yet. You might have needed some coolants. So it was easier technologically to design Webb than it would be to design something that covers those long wavelengths at the size and discovery space that you'd expect to get with Webb. It's something that we want to do. Trust me, we really want to do this. As an infrared astronomer, I do want those wavelengths covered as well. There's some fantastic molecules and dust features around there, and looking especially at exoplanets. But at the process when Webb was first conceived, exoplanets hadn't even really been discovered yet. It was all about detecting the first light in the universe. And so that's where the science drivers were and the technology drivers and the wavelength coverage were, was to try and go to those very first stars in the universe.
That's amazing. I mean, just to call it first light, that sounds so, I mean, if they had, that would just a phenomenal title to call it first light in the universe. And, so those are the types of things that are really intriguing, I think, to the public, like Hubble taking that ultra deep field image that it did. Do you think Webb might give us something comparable to that?
Yes, an ultra deep field Webb image is planned. And I cut it out of the talk, and I apologize for that, is a simulated Hubble Webb ultra deep field. I don't have time to bring it up now, but that does exist. The great thing about Webb is the Hubble ultra deep field took days and days and days to observe, but actually doing a comparable deep image with Webb is actually going to be a matter of hours. So it's over a factor of 100 difference in terms of sensitivity in trying to get that same comparable data. Obviously, we're not going to spend a few hours on it, but actually we're going deep and staring at the same patch of sky as the Hubble Ultra Deep Field with Webb. And the results from that should be groundbreaking. It's what Gillian Wright, the PI of the MIRI instrument, is actually very excited for, is seeing that first ultra deep field image. It's going to be spectacular, and it's going to really, you'll be able to see a lot more details in the nearby galaxies, but you'll be able to see much further away. So the Hubble Ultra Deep Field, where you can see lots of galaxies in there, you'll see even more galaxies with Webb, and I think that's going to be amazing science from that.
I hope you will agree to coming back again, maybe 6 months after launch, because you just have so much excitement for this mission. Of course, we've all been waiting with bated breath for quite a long time for this, but it's so exciting to have you, who I know is going to be working closely with Webb. So we've got another question from Aparhito, who asks, also kind of related to Spitzer, how can Webb help us look at higher redshift galaxies, more than Spitzer could, because Spitzer looks at longer wavelengths than Webb?
It's all about the collecting area. This is where that 80 centimeter mirror versus the 6.5 meter mirror makes a difference. You just have a lot more photons coming at you. We've improved the detectors since then as well. So both the combination of detector sensitivity and just the collecting area of Webb makes a wide range of difference. So while they operate at the same wavelength range, you just don't have the sensitivity before. You couldn't get even close to detecting the photons of those very early galaxies. This is where the size of the telescope makes a difference, and this is why my How to Win at Astronomy covered both big telescopes and new wavelength ranges. So even in the same wavelength range, you just need bigger telescopes to make these new discoveries. And so the size of Webb should be enough, hopefully, if everything goes right, to be able to get the sensitivity, because as you go further and further away, those galaxies are rarer and much harder to see, and much, much fainter. And so you need your big collecting area of the primary mirror to detect those very first galaxies. And unfortunately, Spitzer, as much as I love Spitzer, and I really love Spitzer, it just wasn't quite up to those really, really early first light galaxies. It did very well though.
Yeah, I know. Everyone has their favorite and wants to, have that put in this talk, and it's great. But the current favorite right now is Webb, and so we're going to be wrapping up now. But I thought I'd ask if you knew, when is launch, and do you know what time and how people might be able to view it?
Launch is going to be, I think, at 12:40 in the afternoon on the 22nd. It should be live streamed. I know there's several events planned throughout the UK. Oh, I think they were planned throughout the UK, but now I think many of them have gone online. But yeah, it will be broadcast live that day. I am going to be a very nervous, excited wreck, looking forward to this, but also slightly terrified. I hope you'll get to enjoy watching it. I want it, so it's around lunchtime on the 22nd, and it will always be that window. So if the weather comes in, if there's any, it's always around lunchtime, UK time.
Just amazing. We have a lot of questions. I have copied them. I'll send them to you, and we'll see how we can do about answering them later. But I think that's it for today. We have lots of people who are just thanking you for such a wonderful and exciting talk. Thank you so much for being with us. Did you want to say any last words before I wrap up?
I hope I've conveyed the wonder that Webb will do. I hope as well that you'll get to enjoy the discoveries alongside myself and other scientists in the next decade. And if you do see anything on the news, do think about this wonderful mission. I'm sure you'll see a few, but I hope the excitement and wonder this telescope will produce has been conveyed, and you're all similarly excited as me.
Well, thank you for being with us, and we hope to hear from you again once launch is gone and you've maybe had some time to have some of the data to yourself, and I'd love to invite you again next year. But this is it for 2021 Rouse Public Talks. We will continue in January when we have Katherine Rayner Evans, who will share with us how she explores astronomy and space through philately, the world of stamp collecting. I hope I pronounced that word right. But anyway, see you all until then. Thank you so much.